Hello everybody, in this video I'm going to be looking at problem number 7 from the Carnegie Mellon Informatics and Mathematics Competition, 2017 Algebra round. So problem number 7 is we have A, B, and C are complex numbers satisfying this system of equations, and we wish to find A times B times C. So we can first sort of get a feel for uh, this the structure of the system of equations, right? Because here from each line we're just increasing the powers of A, B, and C. And so we want to figure out some way that we can use that, sort of figure out a way to get from here to here by multiplying by something or otherwise. And I had been inspired by a previous, I think it was an Olympiad problem, um, to multiply everything by A plus B plus C. Because if you multiply each fraction by A plus B plus C, then you get A squared plus A times B plus C, for example, in this one, right? So you basically get a squared term, and then you just get a factor um, that and then you get something that factors to the denominator. So if we multiply, so in other words, if we multiply this by A plus B plus C, then we would get this A squared, B squared, C squared sum, which is 32, and then we would get another A plus B plus C, because for each fraction, we'll get some A times B plus C divided by B plus C. So I'll just write, okay, so we have that. And so obviously this just simplifies to A plus B plus C is 4, which for shorthand I'm just going to write as a sigma and then A to represent the sum of the variables. So now we can use the same trick for this sum, right? If we multiply this sum by A plus B plus C again, or 4, then what we will get is this line plus A squared plus B squared plus C squared. So in other words, 4 times 32, which is 128, is equal to A squared plus B squared plus C squared, which I'm just going to write as sum A squared, plus 122. And so obviously the sum of the variables squared is equal to 6. So now we have, and notice here we've hit the roadblock, right? Because we can't apply our trick anymore for now. But so we can try relating our two pieces of information that we've gotten. In particular, if you square a plus b plus c, then you'll get a squared plus b squared plus c squared plus some extra information. In particular, and I'm going to be writing on a blank piece of paper now. So we have a plus b plus c squared is equal to a squared plus b squared plus c squared plus 2 times ab plus bc plus ca. And in shorthand, I'll just write this as, I'll write this sum as basically sigma AB. So now we can just plug in our information from earlier, and we will get that the sum of AB is equal to 5. Now let's think about where we've also seen this sum, AB plus BC plus CA. When I see it, I think of the expansion of a polynomial with roots a, b, and c, because its linear term will be ab plus bc plus ca. So at this point in the problem, we're going to construct a polynomial p of x. It has roots a, b, and c, and since we know what a plus b plus c and ab plus bc plus ca are, we can almost expand out the entire polynomial, except for the constant term, which is negative ABC. But notice ABC is exactly what we want. So for the remainder of this, I'm going to just call ABC some other variable since we're solving for it. I'm just going to call it y. So this is just a y. So we have this polynomial and we have our goal here. So we want to figure out some way we can get that. And now what I want to do is construct another kind of sum that is similar to one of the equations we had before. And in particular, that is 1 over b plus c plus 1 over c plus a plus 1 over a plus b. Now we can notice that if we were to find some expression for this, then we could use our a plus b plus c trick again to relate it to a over b plus c plus and so on, right? Which in our case we can find entirely in numbers. So if we could find some expression for this in terms of y, right, in terms of this polynomial maybe, then that would be helpful for us. Well, we notice that since a plus b plus c is equal to 4, then each of these denominators is just 4 minus a, right? This is 4 minus a, and this is 4 minus b, and this is 4 minus c. And if you watched my video on a certain algebra problem that involved sort of fractions and roots and stuff, you'll recognize this sum and the trick that I'm about to do. And that is, if we combine all these fractions, right, in our denominator we will have the expression 4 minus a times 4 minus b times 4 minus c. But notice that is exactly equal to p of 4. That is p of 4. And what is p of 4? Well, that's just if we plug in 4 here, these two terms cancel out, thankfully, so that's just 20 minus y. The numerator will be sort of these products taken two at a time. So 4 minus b times 4 minus c plus 4 minus a times 4 minus c plus 4 minus a times 4 minus b. And that is actually the derivative of p evaluated at 4. Now I know there are non-calculus solutions and you can actually just expand the numerator in terms of and then use the sum of a and sum of b and stuff, but a much quicker way is just to use the derivative. The derivative of p, because if we take the derivative, we get rid of our constant term y, because y is just a constant. I know I shouldn't use y as a constant, but y is a constant, so it goes away if we take the derivative. And so p prime of x is just 3x squared minus 8x plus 5. And if we evaluate this at 4, I believe we get 21. So now we have this expression, and so like I said, we can multiply everything times a plus b plus c. Why? Because on the right-hand side, we can just multiply by 4, so we'll have 84 over 20 minus y. And on the left-hand side, we will have a over b plus b over c plus a, and so on, right? And that's just equal to 9, and that was given information. And then we also have b plus c over b plus c, and c plus a over c plus a, and so on, right? And that's just equal to 3. So the left-hand side just becomes 12. And now we just have a straight-up linear equation for y. And that is 20 minus y is equal to 7. And so y which is A times B times C, is just equal to 13. And that is the answer to the problem. So find ABC. ABC is 13. So anyway, I hope you enjoyed this problem. I certainly did. Thank you for watching this video, and I hope to see you in my other ones.